is a very simple outline. In the first part, I will give you a very brief introduction about this technology, followed by our work related to needleless spinning, and also I will give you an example about how we use our nanofiber for our mass production. The second part is a unique property of electrospun fiber. There is a fiber from the PVDF and also PAN. So first look at the electrospinning. So if you work on the fiber and textile nanotechnology and materials area, you probably know this technology, electrospinning. So this is a very classical setup for making nanofiber using electrospinning. It can be very simple. If you just have a syringe with a needle, a high voltage DC power supply, and also a metal plate, you are able to produce nanofiber. So this setup can produce sufficient sample for scientific research. It offers a number of advantages in control, fiber morphology, fabric structure, whatever. So here I listed the advantages. Based on this, people already found electrospun nanofiber have broad applications in different areas. So in about 15 years ago, people realized this simple design is not able to manufacture nanofiber on large scale. So people tend to special design, what later we called needleless spinning. So the needleless spinning is based on a open surface. It doesn't use the needle as a nozzle. Because of this, the fiber generator have a very important influence on the spinning process. So our work started with, in this area at around 2006. So we have quite a few of designs. So we started with this disc and compare this disc with the cylinder and the ball. So the right mark is our invention. So then we found that the conical coil is very effective for making nanofiber on large scale. Eventually, we identified the cylinder coil will be the best one for nanofiber manufacture. So recently, we also work on other design like curved slot and a special one. I will give you some details later. So this is the coil spinning. It's a label version. You can see the setup is very simple. If we have a cylindrical coil, it's partially immersed into a liquid solution. That's for spinning material. So we can get nanofiber. So we get the international patent on this in 2010, and I can give you a video to show it's working. So you can see all the coil surface is a generator area. It can produce nanofiber in tunnel area on large scale. So this the benefit of the coil is the wire shaped left and right. So this can improve the evenness of the fiber differentiation. And if you look at the electric field intensity, you can see the high voltage area always on the coil surface. No matter how long the coil is, it's always distributed evenly on the coil. However, if you use a cylinder of the same dimension, you can see only the two ends area have the high voltage. Middle area is low. If the cylinder is long, the middle area, the voltage is very low. It cannot generate fiber from the middle area. But the two ends area have the higher production rate, so that's cause some uneven distribution. So over the years, we try many different polymer and found as long as the polymer is spinnable by needle spinning, it can be spinned by our design. And the production rate is really dependent on the polymer solution concentration and also the polymer type. So we can get hundreds and hundreds and even kilos of the fiber in 1 hour, just based on our design. So under the support of Australian government, we built a prototype machine in our engineering lab. So using this machine, we are able to understand what happened on large scale. So what problem we should solve for manufacture. So my group design and manufacture this. We have some subcontracted to the factories. So you can see this is a continuous system, only operated by 2 people. So I can show you a video. So we have a substrate, which is a nonwoven mat. It's passed through the system. This machine contains 2 units. Each unit have 2 coils. So if you look at the coil, the fiber generated on large scale like this. And after that, we have a heater to kill the fiber and also winding system. So we can control the deposit to get a patterned or non-patterned fiber mat on the substrate. So in recent 5 years, we have been collaborating with a company in China for commercialize this technology. So this is the first machine we developed in Shanghai. So this is the whole design. We not only use a coil, we also use a blade. So this coil-like blade have better mechanical stability. So this is a small version for lab use. So the machine has been sold to many different organizations in China. We also sold 1 to USA and 2 others to Australia. So we all get a very good feedback about the production rate, and the machine is easy to control. So more recently, we work on other design. This is an example. This is about a classical design slot. Slot is a combination of needle spinning and needleless spinning. So it have a relatively closed system. So it's very suitable for spinning of the highly volatile solution. So, but the conventional slot is a straight line. We found that if we create some curvatures along the slot, we can improve the voltage distribution. Through this, we can improve the fiber fabric's quality. So this slot can be used to produce the nanofiber from a highly volatile solution. So this is an example where we have a solution containing acetone. So if you compare that with the disk, you can find the solution in the disk system, the viscosity increases very rapidly. However, it's in the slot system, it's very stable. So this is a new design we developed recently. So the difference to the previous one is that it just need a very low applied voltage, but the efficiency is high. We call that Electro-aerodynamic electrospinning system. So the critical thing is we introduced 2 inductive electrode. So that's electrode is very close to the generator. Because of this, the polymer solution is easy to approach the inductive electrode. However, we have an airflow to stop this deposition. So the airflow redirect the fiber and also introduce some shear force to reinforce the stretching process and speed up the evaporation. Because of this, the applied voltage just above the needle spinning, but much less than the needleless spinning. So normally needle spinning, the voltage is around less than 30 kilovolt DC. The current is very low. However, for the needleless spinning, we normally use 70 to 80 kilovolt. But for this, It's around 35 to 40 kilowatt. So easy to operate as well. So we're still working in this area. So with the nanofiber produced, we found it's useful for many applications. So our first product is a face mask. So we found if we combine this nanofiber mat with the mat blown, so we are able to produce nano face mask with a very high efficiency, but the burst resistance is low. So for this face mask, the resistance is about 80 par, so that the mask doesn't need to have a vial, but breathes very smoothly. So we developed this face mask in 2016. On this time, the targeted market is China for air pollution. However, this year, the COVID-19 is an issue. So our mask, hundreds, thousands of face masks are sold out just in a few weeks. So we found it's very useful for against this new problem. So this is about the first part. The second part is a unique property about nanofiber, Electrospinning nanofiber. So first, let's see a slide. So this slide collects about all the technology for making nanofibers. So when I first put them together, I had a very strange question. That was, why do we need to select Electrospinning rather than other technology? In other words, so what unique property can Electrospinning bring to a nanofiber? To answer this question, I think our finding about the piezoelectric property on nanofiber is an example. So in about 10 years ago, we found if we use a PVDF as a material to produce Electrospun nanofiber mat, that is nonwoven memory. If we just sandwich that with two metal foil, we can form a very simple device. So this device, when compression, it generates voltage, several volt, 2 volt to 4 volt, is even larger, depending on the area. However, if we compare that with the commercial piezoelectric memory, piezoelectric film, we found the commercial film in the same state, the output is much lower. It's about 20 to 25%. So we proved that we published the first paper in this area in 2011, and later proved our needleless spinning working in this way and even get a higher output because the higher voltage applied. So here I should mention that for the piezoelectric polymer, it's a raw material, doesn't contain any piezoelectricity. So to get the piezoelectric property, the material need to go for a few steps of treatment. Start with stretching and then powdering treatment at a high temperature, at a high voltage, also the elevated temperature. The reason for this is because piezoelectric polymer contain quite different molecular conformation. Normally in the solid state, we call them crystal faces. For example, PVDF, it has at least 4 crystal faces, but only one faces, beta phase, have the strong piezoelectricity. So the reason for this sort of treatment is to convert the other conformation into beta phase and also make the dipole along in the same direction. However, for our technology, Electrospinning, we don't need this sort of complicated multi-step treatment. Just one step include a high ratio of stretching and also the high voltage powdering. In a very short time, we can get a memory. So this memory have the higher output than the conventional, the memory produced by the conventional technology. So which is advanced. So later we found the nanofiber, Electrospin nanofiber, piezoelectric Electrospin nanofiber can also convert the sound into electricity. So this is the device, first device we developed for this purpose. So you can see it include two electrode, yes, consist of plastic film and also a layer of gold in the inside. So nanofiber is sandwiched in between a large hole in the middle for directly for the nanofiber to directly interact with the sound. So this is the setup we use for testing the property. So the speaker generates the sound, and then a meter to collect the electrical signal. So this is the basic property for PVDF nanofiber mat. So the PVDF mat is sensitive to low to middle frequency of sound. So if we increase the sound pressure level, the output is increased. This is a comparison between commercial piezoelectric PVDF film and also our nanofiber. So it is the same condition. Nanofiber mat always generate a stronger signal. So we use it initially for recording sound. This is a signal recorded from the people say 1, 2, 3, 4, 5, each twice, and a second louder. So you can see all the way from the same sound is very similar, but from different sound is different. So then we can use some mathematics to convert that into a frequency-related wave function. So you can see this is from the same sound, but the different sound is different. Here is a video. You can see how the device records the sound. So it's a device.
2, 3, 4, 5.
All the sound can be recorded clearly, and if we modify this device, for example, use 8 hole rather than a single hole, the energy output will be increased. So here, this example, just a 3 by 4 centimeter square device can generate a 14 volt energy, as with outputs about 20 microwatt. If we just rectify this energy using a rectifier, so we can get a DC pulse. So this DC pulse is sufficient to drive 27 commercial LED, and we also use this energy for organic synthesis. So this is a electrochemistry reaction for synthesis of polypyrrole, polysiphon. We also use this energy for corrosion protection. It all works very well. So we also found electrospinning is a very good technology to release the piezoelectric potential of polymer. So a long time ago, people thought PAN should have a strong piezoelectricity, and the electricity, the property is even better than PVDF. This is because PAN have a larger unique dipole moment than PVDF. However, the conventional technology doesn't support this. So that was why people always thought PVDF is the best piezoelectric polymer. However, when we use electrospinning, we prove PAN indeed have a better output, actually has better piezoelectrical property. The reason for this is because if we use electrospinning, the molecular chain, PAN molecular chain along the fiber length, and it have a zig-zag conformation, actually, sorry. Because of this, the natural group oriented in one direction. But in the real material, so the conformation like this has a helix structure, the natural group oriented in different angle. So that's cancel the dipole moment. So we use XRD and solid NMR to prove this. So more recently, we prove the nanofiber pan nanofiber matter is a better energy conversion converter. It can house the noise into high output electricity, and the frequency range is also broadened. For the PVDF, it's about 500 hertz, but for the pan is broadened to the 1,000 hertz. And the same device size for the pan is generate about 57 volt output with power is about 10 times higher. And compared with the PVDF, the pan have the 40% higher conversion efficiency. So this is my last slide. It's my group blog. If you visit this link or just scan this code with your mobile phone, you can go to the website, and there are sub pages. So you see, give information about our people, research course, our achievement, and also publications. So all my work is done through a teamwork and involved lots of collaborations with different groups, different organizations. Here I should thank their great contribution to our research, and also thank you very much for your time.